Hello, and welcome to episode number 79 of Full Crew. I'm Juan Plaza, your host today, and I have the pleasure and privilege of being also Autonomy Global Operational Safety Ambassador. So, as Operational Safety Ambassador, it is my duty to remind everyone that this Saturday is Drone Safety Day. So, please, if you're involved in uncrewed aviation, find an event in the vicinity where you are in the FAA webpage and try to attend. But today we have a fascinating topic, which is space. And after 52 years since the Apollo 17 mission, humanity is back in the business of going to the moon with NASA Artemis missions. So the excitement about anything related to space is palpable. But before I introduce our speakers today, I would like to thank our sponsors, Carasoft, Victus Technologies, Fly Freely, Akin, Tulip Tech, and Blue Arrow. Today we have three experts in the field of space technology, and each one of them has selected an article uh, that they think it's relevant to what's happening today in the world of space, especially in commercial and industrial applications. And so we have Adrian Thompson, Chief of AI and Data Science from Slingshot Aero, Jen Splaingard, Chief Space and Sensors Officer of Tomorrow IO, and Sahil Desai, Vice President of Product of Fortastra. They each have selected an article to discuss. So let's start with Adrian. Adrian is going to talk to us about how Firefly enables uh, on-orbit processing for moon imaging. Specifically, Firefly is embedding an NVIDIA Jetson module on its Elytra orbital spacecraft to run Firefly's SciTech AI software directly in lunar orbit for the Ocular Moon Imaging Service. I believe that this is a topic um, that is very relevant for what's happening in the moon over the next few years. So with that, I would like to introduce Adrian. Adrian will tell us a little bit about him, and then we will discuss the article in detail. Go ahead, Adrian.
Thank you, Juan. So my name is Adrian Thompson. I'm the Chief of AI and Data Science at Slingshot Aerospace. Slingshot Aerospace does space operations, intelligence, and autonomy, and has a very big footprint in the space situational awareness areas, etc. So I joined Slingshot Aerospace recently, but prior to that, I was in self-driving, in autonomous driving, including for Waymo. And then prior to that, I was in aerospace applications for L3 Harris, where I did work on the Artemis rocket, as well as I've previously worked in aerospace for GE Aviation. So that's just a little about my background. As you said, we are returning to the moon, and I think this is really, really exciting. I think it's an excellent time for us to be looking at what's developing in the space arena. This particular article I've looked at, Firefly Aerospace enables on-orbit processing for moon imaging service with NVIDIA Jetson, is interesting because it's not only a return to the moon, but it actually is showing you that we're beginning to put more advanced hardware on the moon for in a computational sense, but also more commercial grade. So we're simultaneously increasing the capability on the software side, and we're reducing the hardware requirements. The specific application is for moon mapping. So they're looking at continuing to have an orbiter going around the moon and looking at doing image processing while essentially trying to use specialized event detection software on this NVIDIA Jetson to send back the most critical information as opposed to trying to stream all video that would be coming back from the moon. This is obviously very important because the bandwidth limitations getting out that far. It's a quarter of a million miles away, but also it's, I think, an important development because using commercial hardware to do something of this nature in a radiation, a very aggressive environment, in an environment where normally we would have been sending things like $80,000 FPGAs to attempt to do a fraction of this processing. We're now seeing commercial grade hardware evolving all the way up to space. So to me, what what this signals is that we are more rapidly getting to the point where commercial capabilities are beginning to get to space, and it's opening up a door where the barriers to software and algorithms that we can run in space are rapidly falling. What I therefore find most interesting about this is not that it's actually a hardware article, but rather that it begins to herald the falling of the barriers to using more advanced software. And then it begins to place more emphasis on what are you doing about the mission critical requirements of software in space. So I like to think of it as, we finally have a Moore's law for space hardware. We can finally keep up. We can finally accelerate, but what can we do now about the quality of the software to keep up?
Okay, well, I forgot to mention that I am a cartographer. I'm a geodetic engineer, so mapping is close to my heart. So, what is the are you being in in terms of the article? Would you like to elaborate on what specific if you have a target in terms of market for these? I can imagine you're going to generate a product, right?
So this is Firefly Aerospace's application. This is a company that has been essentially gradually building a commercial bridge back to the moon. They were the first commercial operator to land an aircraft on the moon just recently, and now they are building the next version of this rocket, of this system, the Blue Ghost 2, that they are integrating an NVLA Jetson with a Lawrence Livermore lab sensor, and they're using that for the optical imaging and the mapping of the moon. So they're going to have this orbiter that's going to continue to go around, and they're beginning to look at providing GNSS type services around the moon. So again, they're building an entire ecosystem around there slowly. And the fact that they've been able to move a commercial processor out there as opposed to a space grade usually would take you many years to acquire or to order in advance and to go through a very rigorous process of radiation verification. We're now seeing the beginnings of using a commercial off-the-shelf Jetson processor for the purpose of replacing what otherwise would have been a very, very expensive design, hardware design. And they're planning to use this literally for 5 years of operation. So it's we literally the age of commercial space around the moon has literally begun. And I think this is really signaling to us that the barriers have fallen.
Why do you think that then that edge AI matters for space operations in this case?
So edge AI is important for on the commercial side, primarily for bandwidth compression. So, for example, with Earth imaging satellites, we collect a tremendous amount of data, but the radio downlinks that are required to send that data down to Earth, are not able to continuously keep up with that volume of data, and we're putting up more and more of these sensing Earth imaging satellites all the time. Well, the same applies as you go out to the moon, where you begin to generate these large volumes of data, sometimes scientific data, sometimes military or other government centric data. But either way, you have to find a way to pull information from the raw data. And that means, you could either bring it all down to earth and try to, fill a data center with it and try to get it to work, or you can begin to look at which pieces of this information are useful. Half of the time, or very large portions of the time, that you might be seeing blank sky or blue ocean. There might be nothing there. Whereas when you put an edge processor there, you can actually pick out, yes, I see a ship, and I can actually track that ship, and I can signal the location of that ship or other features of the ship without having to send back all of the additional data that would be showing you the waves going by, etc. The same would be the case on the moon. You're going to be orbiting the moon. You're going to be looking at it and doing geosurveys of various types, looking for minerals and for other things. But if you haven't found minerals and you're doing your 27th pass, there's very little value in continuing to just send raw data. Or you can at least prioritize the most important data, so you send that back in real time while logging the other data for when you have more available bandwidth.
Yeah, of course I was glued to the YouTube channel of NASA probably a few hours a day, and there were periods of the blue screen when they said we're using the bandwidth for something else. Like, it's so
Right.
restricted. The bandwidth that they have for communication was so restricted. It was communication, or they were sending stuff. There was no more bandwidth for anything else, including that online broadcasting. So that's one of the things that this will contribute, right?
Yeah. I think this is also uh, one of those places where it's easiest to begin to transition autonomy and these capabilities to the edge. There are future applications where we're looking to close the loop completely on the autonomy of the satellites for their own navigation purposes, for tasking, and for other purposes that would extend beyond that in terms of not just downlink, downlinking in a compressed manner, let's say, but also being able to control the satellite itself. You'd need something out there that would allow it to navigate in a, let's say, a GPS denied environment, or if it's having, if it's trying to, for example, do docking to service or do maintenance, you need some level of autonomy out there, because as you get the satellites closer together, the repair satellite trying to dock with the other satellite, the ground-based sensing mechanisms, radar, optical, etc., become less. Just just the latency alone will give you a challenge, as well as you get closer and closer, the resolution challenges become obvious. Yeah.
Okay. All right. Fascinating. Okay, let's move on to Jen. So, Jen, tell us a little bit about what you think of what Adrian just exposed.
Yeah, I mean, it's really interesting, the concept of edge processing and how important it is now. And one of the reasons we see this in the weather space that I work in too, one of the reasons that we need better latency on any observation to get down to Earth is, in the past, on Earth processing was limited by the capability that we had. And so latency, while important, wasn't as important. And now with AI on Earth, we're able to compute and process things so quickly and model things so quickly that the consumption rate for data has certainly increased, causing the need for latency to continue to improve and be as real time as possible, because we can consume it now and make it meaningful on Earth. So I just think it's really interesting that, we think about latency in terms of data from Earth observations in LEO and GEO, and now we're looking at it on the moon as well, to do real-time processing for mapping, as well as sending that information down to the ground. So really interesting article, and I think relevant to the entire space community in general.
Do you have any questions for Adrian?
I don't have any follow-on questions. Yeah, I was intrigued by, it wasn't really aware of that mapping capability, and just, if you think about a presence on the moon and having to navigate and know where things are, just like you do on Earth, like we take GPS for granted here, the same thing will need to exist there. So it's just really fascinating to think about things from a different perspective. So thanks for bringing that forward.
Thanks,
Okay,
Jen.
Sahil, your turn. What are
Yeah,
the
I mean,
comments?
I'd love to start off with a question, Adrian, for you, which is, as there's a lot of conversation in our space about space data centers, and a lot of compute moving into the space domain. Like, how do you see balancing onboard compute with potentially access to in space compute? Obviously, as you bring that data layer and that compute power into space, the latency will drop significantly, and the ability to access high compute powers will increase. So I'm curious. Obviously today it's not necessarily there, but in the near future, I hope that it will be. So I'm curious how you think about that transition in the industry, and how it affects individual spacecraft needing their own compute power.
Yeah, I guess I'm a little bit contrarian on the value add from shifting the data centers to space, in the sense that many of the technologies required to get us there would also be beneficial on the ground. And so the primary challenge simply becomes the data link from ground to earth and earth to ground. When someone is doing, just essentially querying an LLM, which is most of the software that they're trying to put up there, is basically to run those types of capabilities that we really are using terrestrially. You have generally a small amount of input going up and a relatively small amount of input coming down.
Yeah.
I don't think the data centers are going to solve the bandwidth problem going out, let's say, to the moon, because you'd simply be sending the data all the way to the data center and then having the data center still have to send it further down to the ground. But I do think it's an interesting overall technical challenge that if we are able to solve it, it certainly would mean that we have now a new domain in which to begin to explore commercial opportunities. I'm actually more interested in the manufacturing aspects that we could possibly begin to build out in space, which the capability to put very, very high capacity compute could begin to assist. More so than the need for us to shift terrestrial-based systems up there. If I just elaborate a little bit more on that, the big driver for shifting up there is often quoted as being power. That there's more power up there, but then if you go through the calculus and you look at the temperature requirements for running the sensors up there efficiently, the size requirements for getting the data center up there, you begin to develop technologies like silicon and insulator type chips and very expensive things that you could easily stick into a data center down here. And then as the rest of the compute efficiency that you try to push up there just begins to justify the economic model, it also shrinks the gap between the terrestrial and the space-based system. Yeah. So yeah, I think it's a fascinating thing. Great question. Yeah.
Awesome.
Thank you for that clarification. Now let's move on to Jen article about the coming wave of competition in Leo constellations. And Leo, as you might know, is the low Earth orbit constellation, which is very crowded and is being dominated by Starlink. But many analysts are saying that 2026 is the first year it looks like a true race and not a one-horse show. So Jen, why don't you tell us a little bit about yourself and then help us understand this article?
All right, thanks, Juan. So I'm Jen Splaingard, and I'm the Chief of Space and Sensors for Tomorrow.io. We are a weather intelligence company providing insights to hundreds of companies and government agencies worldwide around weather, giving them actionable things to go do about upcoming forecasts. And one of the ways we feed those forecasts is through operating our own constellation of satellites and weather Earth observation satellites. And that's what my team does. So one of the reasons I chose this article, The Coming Wave of Competition in Leo Constellations, is because we run a Leo constellation. And so while we're not in the same domain as Leo broadband that Starlink is in, we're still, us and every other commercial constellation operator is impacted by the continuing increase of satellites in Leo and the congestion, not only with physical satellites, but in the electromagnetic spectrum. So to just kind of summarize this article, really it starts off talking about how Starlink has been dominating this Leo broadband for so long, and that this is the year that we're really going to see competition ramping up. And just for context, Starlink to date has about 10,000 satellites in Leo for Starlink right now. And I think that's really interesting because if you're in this space, pun intended, of space, you probably know that, and you probably know the amount and that satellites are being launched multiple times a week. But the everyday user of broadband, or even if you're a user of Starlink, I don't think realizes how many satellites it takes to provide that connectivity globally. So just the sheer number I thought was really interesting to highlight. And then, they've certainly been the main player and dominating. And this year, multiple other providers are starting to ramp up their constellations. There are others already up there, but they're in the low hundreds of satellites. And even with ramping up this year, Amazon Leo is only expected to reach about 700. So when you compare that to 10,000, it's a small fraction encroaching into that market. I think what the article kind of highlights is that it's not a fixed pie, if you will, that the demand for LEO broadband and access across the globe continues to expand. And so that pie keeps growing, which is allowing room for more entrants into that market, aside from Starlink. Now, Starlink will likely continue to be the dominant player in this space as they continue to launch satellites. They've got authorization for, I believe, about 15,000 satellites, and their full version of this constellation approaches 50,000 satellites. So compared to the Amazon and Blue Origin and Telesat types around the world, those are going to pale in comparison in sheer numbers. And so the article points out that one of the ways they're going to be able to compete is not surely purely on coverage and price, but also focusing more in some niche type of markets and some specialized offerings, whether that be with DoD or certain geographic regions, and really trying to hone in on a niche or a specialty rather than, trying to take away coverage and market from Starlink, because that's probably just not possible at this point. And I think it's interesting from a couple perspectives that one, this is absolutely amazing. The cost to access space has significantly reduced over time, allowing these kinds of LEO broadband constellations, as well as just the trend in general for all kinds of LEO commercial constellations to be launched. The price to get to lower Earth orbit, mass per kilogram, has really reduced significantly over the last decade and will continue to go down as more competition enters that market. So it's just really amazing in the access that it provides people and getting people connected around the world. But it also provides some challenges where, a lot of commercial LEO constellations are worried about things like congestion and collision avoidance. Not every constellation is equipped with propulsion and the ability to do their own maneuvering and collision avoidance. And it is starting to become very congested. So, just having a lot of awareness and planning around that is really imperative going forward, especially for smaller players in this space. And then there's the congestion in the electromagnetic spectrum. As more and more licenses are being granted by the FCC for all of these broadband and other types of Earth observation constellations to be launched, people are having to figure out ways to move around the electromagnetic spectrum to protect the areas of interest and observations that they are making for whatever domain that it is. So I just think it requires a heightened awareness of what's going on and the ability to plan around it, particularly if you're not the dominant player in any LEO constellation. And then, yeah, I think that was why I chose the article. I just thought it was interesting and relevant in general to the public, because LEO broadband does directly impact the public. And then I just thought the sheer number of satellites, if you add them all up, will approach like over 70,000, particularly just in this LEO broadband space, which is a lot of satellites over the next several years.
Especially because it's the barriers of entry are pretty high for to establish a Starlink-like service, right? The initial investment is huge, and I don't know about you guys, but I'm receiving about 2 or 3 times a day ads of Starlink offering the service for, I think it's $39.99 a month, and it's a very aggressive campaign. I don't know if it's targeted to me for a reason, but I'm starting to get a lot of these ads. I've never seen that before, like a satellite service being announced like a smoothie or or a fast food chain. It's fascinating to see that they're trying to expand, the use base, which at the same time will give them the monetary power to launch more satellites. So the momentum seems to be on their side, and given, like I said, the barriers of entry to establish a competitive product will be pretty tough. This is a fascinating thing to follow up, to keep an eye on, because it's going to heat up. These other companies are not going to allow that to be like a monopoly. They will find a way to launch competitive products. So, Adrian, would you like to comment on Jen?
Oh, absolutely, yes. The first thing that struck me from the article was just the coming risk associated with navigating anything in space. There's a tremendous amount of space junk out there already. We're going to generate a lot more, plus we're going to have larger constellations flying. And just the basic situational awareness to manage them, it pretty much already heralds that we need to make a transition to much more automated space traffic control to close. Right now we have a large amount of human in the loop, pure human in the loop type systems. I think that these types of constellation growth will naturally encourage more of that shift. But how else do you see this kind of growth impacting the risk levels in space, as well as the need for things like servicing and other things to deal with that?
Yeah, I think one thing you mentioned that is really interesting is space debris and space trash, if you will. I think that we the U.S. are getting a lot better at what I would call space hygiene and requiring before you launch something, you have to have a plan to deorbit over a certain lifetime based on the operational effectivity of your satellite. So we are getting better at space hygiene and making sure that there is a plan for deorbit and either burning up or how you're handling your spacecraft over its lifetime. So I think that's a really positive thing. I think globally enforcing that is a lot harder. And, we just talked about Starlink in the US, but what we didn't even touch on was China and the number of satellites that China is launching, not only for, their defense posture, but this LEO broadband as well. They've got more than 25,000 satellites approved for this, which is just going to congest the space more and likely not adhering to the same hygiene rules that we are. So, I think there is a call and a demand for space policy that is more global than, country based or even allied based. That we have a long way to go, I think, to get there. Claiming a stake on a sovereign domain on land is a lot easier, and controlling that is a lot easier than the vastness of space. Yeah. So I think that's a problem to be solved still, and one thing that this highlights. And then I mentioned the other two of concern for me is really the maneuvering. Not all LEO constellations have ability to maneuver. So what you were talking about with autonomy and trying to automate the collision avoidance and monitoring in general would be a place we need to go, and management of the electromagnetic spectrum. We are going to run out of bandwidth at some point or run out of bands across the spectrum that aren't being dominated either by these broadband constellations or other types of observations that are being launched. Yeah.
Okay, Sahil?
Yeah, I mean, this is a super interesting article, and obviously one that touches at the core of the direction Fortastra is going in. Kind of talking about the great powers battle right now between China, the U.S., Russia, and space. As a commercial provider, an intelligence provider, Jen, how do you think about the risks that your business is up against, as you kind of think of a lot of generals in the Space Force talking about space being the next contested domain? Potentially that's the domain that we'll see a lot of aggressive actions for the first time in our history if we were ever at conflict. I'm just kind of curious, how does your company think about that risk, especially in this context of more and more technology, more and more investment at the end of the day, moving into this space domain, especially in LEO?
Yeah, it's a really great question because I think a lot of times we think about that risk in terms of only military assets. And there is a push to commercialize a lot of information, whether it be in the civil domain of the government or the military domain of the government. And that puts commercial constellations at the same level of risk when someone realizes that they're providing that same kind of information. We are definitely monitoring this risk, and one thing to think about. Yes, these assets are expensive, but they're not as expensive as, like a military asset at Geo or some other major target. And so I think what LEO constellations kind of do is proliferate a little more and make the targets more dispersed and harder to have one shot knock out an entire thing. So I think that diversification actually is a mitigation in itself. And then the other thing is not any one of those assets provide a sole capability. It's the collective of them, and not any one of those assets costs billions of dollars. They are, easily replaceable. And in fact, one of the things we do is actually build margin. Like we build satellites that have margin because, not only if they were to be attacked or collided with for some reason, CubeSats are finicky and sometimes they don't always work. So there's a couple of ways to mitigate this risk, but it's something that we'll continue to monitor and come up with other ways in the future. Yeah.
Awesome.
Yeah.
Okay, thank you. Well, we're moving to Sahil, our last article of the day. And this is interesting because one of the things that Jen said, it was a side comment, but I think it was very important. Satellites that do not have maneuvering capabilities. And I think that's the majority, if not all of the Starlink satellites, right? They're shoeboxes, right? They don't have maneuvering capabilities, I don't think. So you want to comment on that, Jan?
So the Starlink satellites are not CubeSats. They are quite a bit larger. And I can't speak to all of the capabilities of those, but I would be surprised if they didn't have some maneuver capability. I mean, you risk losing your allocation of propulsion on board, but yeah, not being an expert in that, I don't want to comment too much, but I'd be surprised if they didn't have some kind of capability.
So when you said satellites that do not have that capability, what do you mean? What do you mean by that?
I mean, a lot of CubeSats do not, like small, small 6U, 8U, and even some 12U CubeSats. There's just not enough size, weight, and power allocated to allow for propulsion. And typically they're, quote unquote low cost. And so they're trying to minimize that. Yeah. So the much small ones that are like shoebox size that you mentioned, but Starlink is definitely not shoebox size.
Okay. This next article that Sahil brought to the table, it's linked to that because it's Space Command pushes new warfighting model built on moving satellites, and the premise is that U.S. Space Command, which is the latest force being created for the U.S. Army, is pushing a shift away from large, mostly stationary satellites towards maneuverable spacecraft that can reposition, dodge threats, and complicate an adversary's targeting calculus. It's linked to what we've been talking about, the democratization of space. I mean, the costs per kilogram are dropping dramatically, and that is not only happening in the U.S. I'm sure that is the case in China, Europe, Russia. So everybody is finding ways to reuse more, right? I mean, most boosters today are recovered, and that means that space is becoming um, more easily accessible to
Accessible.
cheaper solutions. Something similar is happening in theaters of war today with drones, right? I mean, the cheaper solution it prevails because you can have more of them. So, Sahil, why don't we tell us a little bit about yourself and then about the article.
Yeah, so thank you for the time. I'm Sahil Desai. I am the VP of Product at Fortastra. A little bit about my background. I'm a former intelligence community officer, and then I, did that for several years, and then most recently worked in the advanced manufacturing domain, scaling munitions at a company called Divergent. And now, most recently, in the last couple of months, I joined an early stage company called Fortastra. Um, we are a company that's building the first private security force in space. And kind of core to our approach and our model is this idea of low cost proliferated maneuver. So the timing for this article couldn't be any better as the Space Force is kind of recognizing a change that they have to consider as they look to their next generation programs. And I think before I talk about the article, there's probably a few pretty important changes in the space domain that we have to recognize to understand why are we moving in this direction. And one, to your point, Juan, space access is changing. And this is to Jen's point earlier. Not only, like, for the first time in history, you don't have to go through the government of Russia or the government of the United States of America to go get access to space. And that's fundamentally changing, not only what gets deployed into space, but who gets deployed into space. And then we look at conflicts in Ukraine and Iran, and we're seeing that oftentimes the things that get targeted in addition to military installation is commercial infrastructure. Iran, as an example, targeted Amazon warehouses. They've targeted US businesses via cyber attacks. And Ukraine has done the same thing. And so the warfare that we anticipated is it's more gray. There's a mix of commercial and defense assets that are held at risk in timings of conflict. And on top of that, the Space Force is already looking to climb up from a hole and protecting their own assets. And really, there hasn't been as much done to protect commercial assets. Something that once again Jen highlighted, the Department of Defense, Department of War is looking at more and more commercial assets, commercial providers to provide them with intelligence. So there's this kind of this dichotomy and challenge that's surfacing of, hey, commercial assets can be held more at risk. Right now, we barely can protect just defense-only assets. How do we go solve this problem? And so I think this article really covers a pretty sizable shift in strategy that the Space Force has encountered. For the last 2 decades, we looked at very exquisite, high-cost satellite assets in space. These systems were not dynamic. They were 5 to 10-year development cycles. They didn't have the maneuvering capability, and quite honestly, we operated with this doctrine that the space is a peaceful environment. It's not contested. It's not congested. And we're finding that with the push of Chinese and Russian aggressive spacecraft, ACATS, we're seeing that doctrine is now challenged. That there's no questioning that the next conflict between major nations, there will be a space component to it. Because if you think about how our military fights wars, the first step is in space. You gather intelligence, you do your communications, you gather your taskings, your missile defense, your missile warnings. All of that comes from space-based infrastructure. And we're only continuing to move more of that infrastructure to space. And so I think, the way that Fortastra is thinking about this problem, I think the best analogy is the drone analogy, in my opinion. About 7 years ago, the Air Force and the military at large was asking itself, how do we go from these really exquisite F-35s, B-21s, these major programs that cost billions of dollars, hundreds of millions of dollars of units per unit, to a lower cost model? And the thing that was invented was Combat Collaborative Aircraft, CCAs. And these essentially became F-35 flights. They were smaller, slightly cheaper, still expensive, right? Still $40, $50 million a unit. And then what we really needed, though, and that's only surfaced in the last year or two, are extremely low cost drones in the $50,000 to $100,000 range. I think right now that is the shift that we're going through in the Space Force, where we've gone from extremely exquisite to this middle tier of capability. But there's still this broader question of really how do we get extremely low cost systems into space? That way, if we were in a state of conflict, we had the ability to respond, asymmetrically with some kind of advantage. And that's the problem set that we're targeting. And we have a pretty important role, I think, in changing the calculus of, I think taking this doctrine that's in this article and taking it even a layer further of, moving past these still mildly exquisite systems and into a new regime of technology, capitalizing on, Jen's article about proliferated fleets of spacecraft. We are finding ways to do things cheaper. To Adrian's point earlier, we are finding ways to bring compute on board for cheaper and less exquisite ways. There are methodologies that we can begin to integrate to bring our cost per spacecraft lower, and then enter these proliferated regimes. And then ideally, if we're successful in that, it's commercial organizations, defense organizations, they both benefit from this type of technology in space. They will have a protector that is commercially operated. And the way, we think about that is kind of like a bank. If you go build a bank tomorrow, the first thing you do is create fences. You get cameras, you hire a guard force. And when we're looking at, hundreds of millions of dollars of space infrastructure, we need to have a similar mindset. And Fortastra is really hoping to fill that gap. So that's a little bit about us. It's a little bit about, why I chose the article. I think it really spearheads a new framework of thinking in the space security domain.
Okay. Yeah, that's it's Taranto all over again, right? And for those of you who study World War II, Taranto, the Bay of Taranto became the day when the battleship disappeared from the face of the budgets, because these swordfish biplanes from the Royal Air Force sank a bunch of Italian battleships. And everybody was in love with battleships in 1940, right? Hitler, Churchill, they all have their battleships. And suddenly these planes destroy that. And something very, very similar is happening in Ukraine when a commercially available drone drops a grenade into a T-34 tank, a $34 million tank. Who is going to invest in tanks anymore? I mean, it's right now we're in the middle of that shift. We don't understand it yet, but if you add the space component to that complexity, it's great, because when you said space, you mentioned major. You didn't say every country in the world. You said major countries war, because it's still an exclusive club, right?
Yeah, but soon it might not be, and so soon you might have, in a competition between Chinese companies and American companies. Once again, like that access is opening up, and there aren't as many rules of engagement between commercial firms or non-state actors who potentially also have their ability to access space. So I think today we feel safer because it's really predicated on major conflicts. But once again, as the barriers of entry eliminate and more, and we saw this once again when ISIS was buying off-the-shelf drones and putting packets of C4. We never thought years ago that any terrorist organization would be that competent or that capable. And then within months, they began, implementing that technology and doing it very, very quickly. So, I mean, I hope that never happens in space. And that's, every one of my colleagues, we pray for that future. But the reality is that that's the direction that currently space is heading to, and we just feel the need to have to prepare for it.
Even the
Yeah.
Hamas incursion into Israel using, paragliders, uh, very low flight, non-radar. I mean, it's a demonstration that today the amount of cheap tools available to everyone, it's really scary, and investing billions of dollars in this huge infrastructure is might not be the best use of the defense dollars. But okay, let's
So
Adrian, go ahead.
yeah, so I was going to kind of build on something Sahil said, yeah, because the the pattern we're seeing with, like I said, migration from exquisite hardware. We've seen this in space, as Jen mentioned. We used to have very expensive billion-dollar assets. We've brought them in closer. We're cutting bandwidth, and we're also cutting costs. We're shifting more towards attritable assets that are going up there. We're expecting less of them. They sometimes can't navigate, sometimes can't propel themselves. We're expecting more coordination around them instead of them coordinating themselves. And we're shifting more towards a system where it's as if hardware is getting cheaper for all these applications. You mentioned multiple warfare applications, but even for the just basic commercial applications, the hardware itself is getting cheaper, and we're finding ways to squeeze more commercial off-the-shelf hardware out there. But we're depending more on very sophisticated software, communications, and networking to make these into warfare capable systems. We're seeing this in Ukraine, where they're basically coming up with different ways to deal with jamming. They're coming up with different fiber optic systems, and they're trying to find ways to integrate and coordinate the software. So increasingly, software is becoming that mission critical layer that is enabling the cheaper hardware to be effective. This is actually why I actually picked the article I did earlier, because it's almost as if the last barrier to entry to COTS hardware, it used to be, well, you could use it on the ground, but you can't use it in the air. Then we started using it in the air. So, okay, well, you can use it in the air, but you can't use it in space. We started to use it in LEO. Okay, well, but then, for sure, you can't use it in deep space. And now we're saying, no, 5 years of an operation. So the barrier to entry, this is what I said, we've done a Moore's law now on all the hardware. We've done all the transitions. The hardware is pretty much converging to a situation where anybody, almost any person on the planet now can conceive of, building themselves a space asset. And your children in school can be doing projects to send up a CubeSat. I mean, this is real, right? So increasingly we're shifting to an environment where there's a strong dependence on autonomy to control the number of assets, on software to manage them in these increasingly hostile environments. And so the piece of the discussion I'm not hearing, and why, and as I've gone through even these 3 articles, I've seen kind of that same theme of, we want more we want more independent, autonomous satellites that can move out of the way. We want them to, we want to use attritable satellites or others to intercept. We're getting back to this point of, yes, but how are you going to control all of this? You're going to have a very, very massive network. Many of these will be more difficult to see. They're getting smaller because you have the commercial hardware. So I'm seeing this very powerful trend. And I guess for me, the big concern is, now that we've got Moore's law for hardware, are we going to end up with Murphy's law for the software? Right? Are we really getting ourselves into that? So like I said, Sahil, I didn't want to steal your thunder on that, but I felt like it was very, very important for us to address this piece of the issue. How do you see that from your side?
I mean, here's the truth, right? Like, when you think about the fleet necessary to provide just the defense and security mission, you're talking about hundreds to thousands of smaller, low-cost systems. You can't have a human operator scale for every one of those individual satellites. More importantly, when you layer degraded or contested environments like we saw in Ukraine, we have to assume with that assumption that will come to space. These platforms, they need to operate agentically. They have to be able to rationalize and reason and act, with context, on the edge, compute, make decisions. And I think that's why, I pressed you on, how do you think about onboard compute versus layered compute in orbit, is that ultimately I think we can't deny that infrastructure is going to move to space. More and more and more infrastructure is going to move to space. And I think if we continue down that motion, we have to have the ability to have these smart systems think about problems and solve them without always being tethered to a ground link. And I think that's going to push a new layer of software autonomy, similar to what we see with Claude and OpenAI, chatbot reasoning. We're going to see that really start to penetrate the autonomy world, where we go from very task-based autonomy, like do A, then do B, then do C, into hey, your general mission is this. Reach out to me if you go outside those parameters, right? So, you position a satellite at, to shadow or protect a fleet of spacecraft. You detect something coming towards you, go intercept it, monitor it, and then figure out what you need to do and let me know. I think that's going to be the future that we have to move to. And I just, once again, want to reinforce, like, the supply chain is changing, Adrian. You raised a really good point of, like, we do not have to think about space supply chain through the traditional lens that we always have. We have the ability to push the bar, to push the growth of the businesses that we rely on, and get their technology and integrate it into space. And I think we're just going to continue to see that trend, and I think it's the right way to go.
Okay, Jen, any comments?
Yeah, just one, interested, Sahil, in your thoughts on the trends that this, maneuverability is driving from a technology or alternatives to just good old propulsion, whether it be, alternative methods or refueling stations, or, what trends do you see this need driving in general?
I think, once again, like, from my view, you need a mix, right? Like, you can't have a single architecture that dominates it all, right? F-35s, F-22s, they have their role to play. Attritable systems that don't have refueling, that don't have, are more one-time use, that are lower cost, they have their role to play. And so I think ultimately you do need a mix of on-orbit servicing. You need a little bit of that infrastructure to feed larger systems. And then I think, once again, you if you can get the economics low enough, and the launch economics decrease as they've trended to over the last couple of years, I don't think that every system needs on-orbit refueling. I don't think every system requires, long shelf lives that, have to be extremely rad hardened. We just have to be really smart about when do we apply those types of attributes, those types of requirements on a system, and when do we not have to. And I think that's one of my favorite conversations that I have with our chief technology officer and our CEO almost weekly, is how do we smartly think about and make decisions based on the trends in economics for launch, and the, like, complexity that we drive into a spacecraft.
Awesome.
Well, at least in the world of aviation, I think UTM, the AI, arrived perfectly in time to allow for the uncrewed management, the traffic management systems, the UTMs of the world, to now be helped by by AI, by the ability of these machines to predict where will this drone be in 10 seconds from now, and do that thousands of times. But in the difference with space is that here it's everything is cooperating. You want to operate in this, you have to obey by these rules. In space, you can't do that. So even if we develop a great UTM for space, and we add AI to manage the traffic and avoid any conflicts, you need everybody to agree to certain protocols. Is that feasible?
I hope so. I think from a technology perspective, yeah, there's no technology limitation on it. But what I will say from a conflict perspective, you're always going to have to find, there are always going to be people who don't play by the rules, and we need to be prepared for that.
Yeah.
There is some responsibility to think of protecting your own assets. At some point, with the flexibility to put cheaper and cheaper hardware up there, like you said, you have many people. Even in a non-kinetic environment, you're going to have risk, and that risk is not something you can see transparently through. So, like I said, as people are able to put chips up there, they're able to get software up there, even vibe coding software. And I'm flagging this because I've seen it multiple times. I actually said, as was with the self-driving AV industry, right? Mission critical AI was easy, looked easy until the first major accident. Then it became exponentially hard, right? So, it looked easy in 2008. It looked too easy in 2007. We had all these vehicles moving and so on, and then the real accidents start happening, and then the companies started digging and like I say, okay, so we can't just trust it. And I think one of the both of you have mentioned, agentic AI, agentic. But one of the most interesting differences with the agentic systems and the other AI systems is that those agentic systems, they are not as predictable. They introduce additional randomness that normal aviation grade software testing is not able to handle. It's a very different ballgame. It's non-deterministic. So, like I said, I because I'm coming from that mission critical software area, I see a coming challenge for the many of these things that we're looking at and saying we're going to deploy in an agentic fashion. There is a thorough amount of analysis and testing that needs to go into these systems, and I don't think it's there yet. I think the hardware is getting there rapidly, but I do think we need to switch a bit of our focus and start looking at what does it take to put agentic systems there, to put them into space where the costs of errors are very high, and where you could have long-term issues from if you have a collision and you start generating more and more space junk. Small pieces of debris can cause very large problems for a cluttered space like Geo, as Jen pointed out. So I think that I think there's more of a software play here that is obvious, and I'm waiting for the discussion to transition there so we can actually begin, get real serious about, how do we set standards, how do we adjust our expectations, and how do we make sure we have the right infrastructure from a software basis in place to allow us to do this safely.
And for decades we have lived in a world with, hardware was king, and hardware is easy to regulate because it doesn't change that fast. With software, you might have 2 or 3 versions a week. So how do you add? How do you regulate? Something that you need to be updating every 2 weeks. It's happening everywhere as software begins to invade, begins to get into everything. We see that in every aspect, and the standards of aerospace engineering and software engineering are very different. So there's a little bit of a disconnect there too. But anyway, that's thank you guys. This was so much fun for me because talking about space, it's one of my favorite topics. I would like to thank, before we go, our sponsors again. Really, really thanks to Carasoft, Victus Technologies, Fly, Fly Freely, Akin, Tulip Tech, and Blue Arrow. That's all the time we have for today for our space crew. And like we all say here, we are out of here. Thank you.